Hi, good morning all. I am Dr. Abdul Pasha, working as Assistant Professor, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So here it is about the course Power System Operation and Control. So in this course, today's topic is about Powerfactor in Electrical Energy Management Systems. So we have seen so many cases in Powerfactor cases. So how it will influence the entire power system network, with what variables it is going to be undertaken. These are the things we will suppose to discuss in this case. So coming to power factor, usually we take the power factor as cosine of the angle made between the voltage and current. But coming to the power system network, which will influencing the parameters voltage and current with respect to their angle, means this will be treated as one of the measure how it will be effectively in power system network being utilized. So coming to this case, a high power factor, that means usually we treat the power factor in three cases, like lagging, leading, unity power factor cases. So coming to lagging case, when the power factor is operating under lagging means, so it is operated with low power factor case. When it is operating with leading means, yes, good power factor is operating now. And also we may treat that unity power factors also to be good, as power systems are healthy in conditions when they are operating under unity leading conditions. So likewise, high power factor means usually we treat approximately unity. So which will indicates that efficient use of the electrical distribution system. So proper utilization of the distribution network with good power factors means that is about leading nature. So or you may treat it as unity case. So while a low power factor indicates the poor utilization of the power system network. So your loads may suffer and you may be affected with economical operations of the power system network. So that's why traditional cases will are supposed to be taken for the power factor as in terms of the cos theta. So when reactive compensators of the capacitors or inductors which are situated in the load. So if you treat most of the rotating machines like motors, all the rotating machines, transformers, those may are supposed to be treated as inductive loads in nature. So the current, it may be either lags or leads the voltage. So inductive circuits, most commonly found industrial electrical loading are the current lags the voltage with respect to the time case. So inductance is here mostly created by motors of every type. So transformers pull in the coils for relays, contactors and ballast coils. All are inductive in nature. They may all cumulatively treated as inductive loads. So every electric load that works with magnetic fields. Just now we discussed like motors, choke coils, transformers, inductive heating elements, arc welding generators. All they are containing inductive coils. They are inductive in nature. All they may be treated as cumulatively inductive loads. So they produces varying degree of electrical lag. So this should be variable in nature as the angular parameter. So that should be treated as one of the inductance case. So every electrical load that works with the magnetic fields, like motors, your choke coils, transformers, all these we discussed, producing varying electrical nature. So they are supposed to be treated as one of the lagging components. So when the power factor is 1, means cos theta or phi is treated as 1. So current is in phase with the voltage and the circuit is resistive in nature. Here the thing is that when you are treating power factor as 1 or cos theta is equals to 1, so current is in phase with the voltage. I is in phase with the voltage is. So then the circuit is resistive in nature. If cos theta is 1 means the transmission is about 500 kV in a 400 volts 3-phase system that requires a current of 722 amps. This is the calculation usually we do. So when the transmission of the same effective power at an angle of cos theta is 0.6, then it requires a higher current, like will be about 12,003 amps. So accordingly, so distribution and transmission equipment as well as feeding transformers, they have to be derated for this higher load. So this is usually happen. So furthermore, their useful may also be decreased. This may happen eventually. So usually every electric load that works with magnetic fields, we already know motors, choke coils, transformers, inductive heating circuits, arc welding arrangements, generators, they are supposed to produce varying degree of electrical light. So this may be treated as one of the inductive nature. So as a line current drawn by the inductive load contains two components, like magnetizing current that is denoted with Im and the power producing current that is IP. These are the two components they usually decides. So magnetizing current is the current that is required to sustain the electromagnetic field, or it may be treated as field strength in the whole machine. So this component of the current that should be creating the reactive power, so that does not useful for doing the work, but it circulates between the generator and the load case. So it places a heavier drain on the power source as well as on the power sources of the distribution network. So real power producing current is the current that reacts with the magnetic flux. This is to produce the mechanical output of the motor case. So when the real power is working, means usually we have two combinations, real and reactive power combinations. So real power combination is useful to run the system, and the reactive power combination is to make the magnetic field over the machines of inductive in nature. So real power producing the current is the current that will react with the magnetic flux to produce the mechanical output of the motor. So real power is measured in kilowatts, P denoted with P. Real power is denoted with P and it should be measured in kilowatts, which together with the reactive power means kVAR, that makes up the apparent power that will be expressed in kVA, that means kilovolt amperes. So power factor is the inefficiency expressed, that should be the ratio of active or useful power to the total apparent power, that means kilowatt by kVA ratio is going to be considered. So usually apparent power is always in excess of the active power case. This is for inductive loads and it is dependent on the type of the machine we are going to utilize. So graphical representation we may take for the power triangle here. So this triangle will represent the one of the power triangle case, as one of the sides of the combination may treated with total power as in kVA and another side with kVAR as non-productive power, and the base will be treated as productive power in kilowatts case. That means the whole of the power factor combination can be drawn from the power triangle as the ratio of that kilowatt of the productive power to the total power in kVA range. So this is the combination we usually treat. So cosine of the phase angle, that is theta in between the kVA and the kilowatt components, they are supposed to represent the entire power factor of the load. So kVAR will represent the non-productive reactive power and theta is the lagging phase angle. So with respect to that, relation between the kVA, kilowatts and kVAR is non-linear in nature and it should be expressed as kVA square equals to kilowatt square plus kVAR square. So this is the combination of real and reactive combination. Real square plus reactive combinations. So a power factor of 0.72 would be that should be treated only for 72% of your power that should be consumed, and it is used to do useful work. So perfect power factor means it should contain 1, that is unity power factor. So meaning that 100% of the powering being used to make the useful work. So complete power, that means 100% of the power is being used for do the useful work case. So power factor is also referred to as leading or lagging. In that case of the magnetizing current, so power factor is lagging. In that, current follows the voltage waveform. So amount of lag is the electrical phase angle that should be in between the voltage and the current case. So power factor is equals to the cosine of the phase angle between voltage and current waveforms. So usually we treat this is as general scenario. So coming to the apparent power case, this value is determined by multiplying the current times of the voltage case. So this should be treated as one of the apparent power. So in a 3-phase circuit, usually when you multiply the average phase-to-phase voltage, that should be in times of the average line current, then number of times of the square root of 3 divided by 1000, that gives the one of the apparent power case. So that means units are considered in kVA range, so reactive volt amps. So coming to the reactive power, this will describes the magnetizing requirements. So how the magnetizing requirements means, for a given electric circuit, it should contain inductive loads. Then only it should be treated with the reactive power consideration. So here the value of magnetizing power that should be determined by multiplying with the apparent power by the sine of the phase angle theta in between the voltage and the current is treated. So these units are considered as kilovolt amperes reactive. That means kVAr in nature. So reactive power coefficient as apparent power multiplied with the sine coefficient as theta in nature. So coming to real power coefficient, so this term is what electricians they supposed to deal in considering the plant loads. So what happens here means real power is related to the apparent power. This should be done by the cosine of the phase angle made, as it should be treated as theta. So this is in between voltage and current case. Units are kilowatts. So real power coefficient as apparent power into cosine of the angle made, that is theta is going to be considered. So here we should remember that real or reactive power, that is real or reactive power is measured in kilowatts as 1000 watts. Kilo means 1000, so 1000 watts. So reactive power is measured in kVAr case. So that is also 1000 volt amperes reactive in nature. So total power is measured in kVA means 1000 volt amperes are going to be considered. So typical unimproved power factor by industry means then it should be treated as with a simple table contains representing all the loads that we supposed to see now. So that typical uncorrected power factor is done by different sectors of the industries. So that we supposed to see in this table. So here industry is represented. With respect to that, power factor is going to be considered. For considering auto parts, it should be about 75 to 50, and more than that 80 will be considered. And that should be for bravery experiments, then it should be 75 to 80 it should be considered. And for cement industry, it should be 80 to 85 considered. Chemical industries, it should be about 85 to 75. And coal mines, it should be 85 to 80 range. And clothing arrangement, it should be 35 to 60. Electroplating, it is about 85 to 70. Foundry equipment, so then it should be about 75 to 80. Fogging experiments, then it should be 70 to 80. Hospitality, it should be 75 to 80. And machine manufacturing cases, 60 to 65. Metalworking, it is 65 to 70. Office building equipments, 80 to 90. And oil field pumping cases, 40 to 60. Like plant manufacturing industries, they supposed to maintain the power factor about 65 to 70 Ks. And plastic type of arrangements, they treat industry 75 to 80. Stamping cases, they take 60 to 70 range. Steel works, they treat usually 65 to 80. Tool, dies, jigs industries, they treat 65 to 70. So all the industries, whichever it is supposed to be listed here, they supposed to be operated in between the range of the power factors at suitable conditions. So typical uncorrected industrial power factor is supposed to be treated at a range of 0.8. So what happens with this means? This means that 1 MVA transformer can only supply 800 kilowatts. 1 MVA transformer can only supplies 800 kilowatts, or it should be considered that a consumer can only draw 80 useful amperes from 100 amperes of the supply. So to put it the way other, in such a manner that 3-phase 100 kilowatts load would draw 172 amps per phase. This should be treated instead of 139 amps expected that current. So inherently low power factor equipment, utility company has to generate much more current that should be treated than its theoretical required. So for example, in instant manner, we say that in a situation where real power demand, that is in kilowatts, at two plants is same. For example, if you treat two plants, then real power demand at the two plants are same. One plant has an 80%. Then how it should be the differentiation means power factor while the other has a 70% power factor, that utility must provide 21% more current. This should be to the second plant to meet the same demand requirement. So this excess current will flow through the generators, cables and transformers. In the same manner, they do the useful current aspect. So if steps are not taken to improve the power factor of the load case, means all the equipments, conductors, transformers, they are serving the second plant that should need 21% more carrying capacity. This should be treated than those provided to the first plant case. So we should take the proper suitability of the power factor of the load. Then when all the equipments of the conductors and transformers, they should not read to the second. So they should meet to the needed requirement of the required percentage that should be carrying more capacity than the provided to the first case. So additionally, resistance losses like I square R in the distribution network of the conductors, they should be treated 46% greater in the secondary case. So this must be considered according to the requirement case. So this greater of the case will treat additionally as one of the heat loss. I square R means one of the heat loss consideration. So this should be more in the distribution of the network, as the conductor should be 46% greater than in the secondary case. So here, when utility is paid primarily, this is based on the energy consumption and the peak demand is supplied, then without a power factor billing element, so utility would receive no more income from the secondary plant, and that should be rather than the first case. So to discourage these insufficiencies and to compensate for the burden of supplying extra current, so utilities usually treat establishing power factor penalty. So power factor penalty will be treated for the utility case in their rated schedules. So these penalties may treat on electricity bills, as their reactive power charges are going to be considered in terms of their kVA maximum demand. kVA maximum demand or kVA availability charges. So these charges are must considered. So for instance, it should be known that information taken from the billing about electrical systems are considered. So as electricity authority, they deduce the bills, and according to that how the power factor is going to be operating. So based on that, the reactive power charges are going to be considered. Once the utility is paid primarily, so based on the utilization of the energy consumption, then total peak demand is ready to supply. So all this process will happen without having that power factor billing amount. So utility is ready to receive no more charges from the second plant when it is compared with the first case. So to make sure about all these considerations for compensating about the burden of the entire extra current, so usually the consumers are typically establishing power factor penalty considerations in their rated schedule. So this may charges appears as indirectly on the electrical bills as one of the reactive power consumption charges. So this should be considered according to the kVA maximum demand with respect to the kVA availability of the charger. So when the information is to be taken from the billing authorities, then this should be charged accordingly. So when there is a consideration of kVA about 1000 and kilowatt is about 800, kVAR is about 600 and the power factor is about 0.8, then typical utility building structure will be given with a suitable example here. So with the consideration of above values in kVA, kilowatts, kVAR range and also power factor range, 90% of the building structure is considered. That means demand build is based on the 90% of the kVA, or we may treat 100% of the kilowatts, whichever is supposed to be higher. So because of the facility has a power factor about 0.8, they supposed to pay demand rates on 90% of the kVA. That means this should be treated with 1000 into 0.9, that is about 900 kVA. So because of this larger number as consideration with 900 kVA greater than 800 kilowatts is going to be treated. So what is happening with this consideration means facility is paying a penalty on 100 kVA of unproductive power case. So this will be the penalty charged as on 100 kVA of the unproductive power case. So as correcting the facility's power factor to 90%, and it should be aided to eliminate this penalty cost. This may be treated as one of the simplest condition to deal with all the structures of the power system network. Similar case when 100% kVA plus 100% kilowatt building structure is considered. Here one rate is applied to 100% of the kVA and another rate is applied to 100% of the kilowatt rate. That means both are then added together to determine the total demand charged on the billing structure. So when they are added together means that will specifies the total demand charges. This will be reflected onto the bill directly. So if you suppose to ready to make the correct the power factor to the unity case means, then kVA required will becomes equals to kilowatts or 800 kVA, which is equals to 800 kilowatts. So we can recover costs paid on 200 kVA at one of the kVA rates they are assumed to be equal, and this rate is being paid for kVA and also kilowatts. That means we need to correct to the power factor to the unity case. Otherwise, then power factor cannot be operated properly. So this should treat to the equivalent kilowatts range when we should suppose to recover the cost paid on the particular amount. So we should assume equal rates that should be paid for the kVA and kilowatts ranges. So rather than paying demand costs on 1000 kVA plus 800 kilowatts, when it is the total combination 1800, then the power factor is equivalent to unity. We will pay demand costs on 800 kVA plus 800 kilowatts, which is about 1600 range, and saving will be treated as this total 1800 minus 1600 which is about to 200 Ks. And here we should remember that one of the noting condition, generally cost per kVA is greater, that means higher. So this should be treated than the cost per kilowatts. So thus the saving should be greater by correcting the power factor to the unity. So when you are going to treat for the cost per kVA, which will be higher than for the kilowatts of the cost rate. So it should give the savings that should be higher. This should be treated by correcting to the power factor to the unity case. So reactive power charges are one of the penalties in the billing. They should always be regulated, and excess reactive currents and associated charges also to be removed by well established technology that is called as power factor correction. That means excess rate currents means these are going to be associated charges. They can be removed by well established technology, and when you are adopting well established technology means that will comes under the power factor correction means. If you are not making suitable power factor correction means your authority may ready to face the charges, and that should be directly or indirectly implying on the customers. So this will suffer in electricity bills more. So to come across with that, we should implement power factor improving devices like capacitor banks across the lines, improving the distribution system efficiency, and adopting new technologies, how to correct for the power factor devices. So these are the aspects we must treat. So according to that only you can ready to make the power factor correction. Otherwise the billing charges are more and the utility will suffer. Then authority is ready to charge extra more on unit cost. So all these must be treated. So we need to treat rather than paying the demand cost, you should treat the savings in the entire electrical charges. So unity we will pay demand cost on the given kVA and kilowatt range. That resultant only gives the saving of the power. So it may be kVA greater than the cost of the kilowatt range. So that's why saving should be greater by only correcting the power factor to the unity case. So this we must treat to make the power factor of the correction devices into the systems. So if you treat keeping this technology offsets to the inductive reactive currents, they are supposed to introduce equal and opposite capacitive reactive currents. So what happens to this equal and opposite means they try to cancel each other. So typically this can reduce the electricity bills about 5 to 8%, and with this payback period of 12 to 18 months, in addition to that consumer shall gain from improved supply availability. That will improve the voltage, reducing the power loss quotient, and healthy conditions are achieved from this all these aspects. So these are the key issues we supposed to treat for making the power factor correction of the device. So here to improve the power factor, the equipment drawing the kVAR of the approximate same magnitude as load kVAR but in phase opposition, leading is connected in parallel with the load case. That means resultant kVA is now allowed for smaller and the new power factor as cos square theta is increased. So likewise any value of the cos square theta can be obtained by controlling the magnitudes of the leading kVARs added to the system. So it is never economic to attempt to improve the power factor to unity, but since the nearer to the approximate to unity more than the kVAR must be installed for a given improvement case. So likewise power factor in electrical energy management is treated mostly. So these are some of the references we can make sure about for more information with some other videos. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.